should be recording, and I'll record it this other way. It doesn't look like the Blackboard recording works very well, but my goal is to post the recording on Blackboard. Didn't really realize I could post videos on Blackboard. So my goal is to post this, provided that the video records properly. My goal is to post this on Blackboard, but to have it live so that you can ask questions as we go along as you normally could if we didn't have this online issue. Okay, so again, simple linear regression. The goal is basically to fit a straight line through a set of data. Okay, and so for the simple, basically just means we have two variables. One is kind of the variable that we're interested in, the outcome variable, the response variable, and the other variable is a predictor variable. So the goal is using information from the predictor variable, can we gain information about the response variable? Okay, and specifically we would like to fit a straight line. And of course, epsilon was our random error term, which takes into account the fact that there's not a perfect relationship between y and x, but hopefully that there is a linear relationship of this form. So we said if the expected value of epsilon is 0, then the expected value of y is just this beta naught plus beta 1x, right? So just the intercept plus the slope times what x. And so even though x is what's called the predictor variable, the predictor variable is always assumed to be known and observed, okay, which means it's not random anymore. And so we talked about beta naught as the intercept, beta 1 is the slope. We looked at this waste example last time. And so we have two variables, right, an x and a y, predictor variable, response variable. And so we can look at a scatter plot. It's a very common thing to do when we have two variables. And we can clearly see that it looks like as filtration rate goes up, the moisture percentage goes up. So it looks like a simple linear regression model might be appropriate for this data. Now in general, there are lots of different ways, lots of different models that you might choose for a set of data. Each is going to have benefits and weaknesses. Okay. The best thing about simple linear regression is that it is easy to interpret. Okay, so oftentimes this is a pretty small data set, a pretty straightforward looking data set, but oftentimes you might be able to choose a more complicated model, and we'll talk about some more complicated models later on, but you can choose more complicated models and they might fit the data better, but usually at the cost of interpretability. Okay, the complicated models, the parameters such as in this case beta naught and beta 1, they don't have nice interpretations, okay? As they do in simple linear regression, right? Beta naught is the intercept, beta 1 is the slope. And those have really nice interpretations in real life. But if we start fitting more complicated models, the interpretations kind of go out the window. So sometimes you have to choose between the trade-off of is it more valuable to have a more accurate model, or is it more valuable to have a model that is interpretable, okay, and easy to relay the information from one person to another? And often that could just depend on the application. So we talked about least squares estimation, right? This is the basic gist of how we're fitting this line, right? Our goal is to fit the best possible line through the scatter plot. And if we're doing a simple linear regression model, we want to fit the best line. And of course, well, what is the best line, right? We have to quantify that, and least squares is how we quantify that. We want to minimize this function, which I tried to explain last time, is just nothing more than the squared distances from each data point and the line that we're trying to fit. And so we want to minimize those distances. And we do that with derivatives, and this is what we would get, but not super concerned with that at this point. And so usually we put hats on things, on estimates or estimators. Again, I technically would rather have like a beta naught hat and a beta 1 hat here, but that's not what the notes uses. But the y hats are what's, you could call those the predicted value of y or the fitted values. So for this example data set, the red line here is our simple linear regression model line, right? And we do that in R. And again, we'll look at today, we'll actually do this with a data set. But we can see that we have beta naught hat, the estimated intercept and the estimated slope, which give us our red line, which is just this. And so anytime we have a filtration rate to plug in, our regression model will spit out a moisture prediction. So it looks like here, if we want to predict the moisture level when the filtration rate is 150, we just have to plug in 150 into the filtration rate, and then we just have 73 plus 0.04 times 150, right? And that spits out a number. And what that's going to spit out, right? If filtration rate is 150, like right in here, the prediction from the model is just going to be the y point wherever that x is on the red line, right? So if filtration rate is 150, right, then it looks like it's going to be slightly above 79 maybe, or right around 79 is what the prediction is going to be. And we can see then that's what it is, okay? So some assumptions we briefly talked about. We want all of these assumptions are going to be about the random error term epsilon. Okay, so if we think about having an entire data set, we can just label each observation with basically a subscript I. So if we have 20 observations, little n would be 20, and we would have y1, y2 up to y20, and x1, x2 up to x20, and then same thing with the epsilons, the random errors. And so again, the random error, it just accounts for kind of the randomness in the population, but we would like these random error terms to all have expected value 0. So, and we would also like them all to have the same variance, whatever that is. It's not known, but we would like them all to have the same variance. And we would like the random errors to be independent and normally distributed. So, of course, we know what a normal distribution looks like, right? It's some bell-shaped curve. And so we would like essentially each of these random errors to have a bell-shaped curve, them all to be independent, right? The random error from one observation shouldn't affect the random error from another. And when we would like these normal distributions to be centered about 0 and all have the same variance, okay? So basically, these random errors are not going to depend on the values of x and y, kind of, for example, right? It doesn't matter what the x value is. The random error should just still be some random error term, not affected by the value of x. Okay, I will show you later on, there is a nice way to summarize all 4 of these assumptions. So that is something kind of to remember. There are technically 4 assumptions that are going into this simple linear regression model. All 4 are with respect to the random error term, but we can actually summarize all 4 of those into one statement, which I'll get to in a little bit. Okay. Okay, so with these assumptions on the random error term, right, this is our model. And again, these are just constants, right? Parameters, just constants. And then x, as I've said, we treat the predictor variable as just constants, right? Because we kind of observe it from a data set. So if this is all constant and epsilon is the only thing that's random on this right side, and we know its distribution, then what we have is that y is equal to some normal distribution, right? Normal distribution plus a constant. And so we don't show that, but that's actually pretty easy to show that this implies that the response variable, y, has a normal distribution with mean beta naught plus beta 1x and a variance of sigma squared. Okay. It's known that the expected value of the least squares estimates, again beta naught hat, beta 1 hat, are technically they're unbiased for the true values of beta naught and beta 1 in the population. And something else, it can be shown that these the estimators, the beta naught hat and beta 1 hat, also have normal distributions. Not worried about this so much, understanding exactly what these variances look like. I don't think that's very important for us. Okay. Estimating the error variance. So we've said, okay, so this kind of sums it up. So all four of these assumptions on the error term are, well, it's normally distributed. Each one is normally distributed. Each one has mean 0. Each one has variance sigma squared. If you just put IID right here, independent and identically distributed, then this one statement would summarize all four of the assumptions on the linear regression model. You just need a IID right above here. And if you look at the solutions to homework 5, which I sent you this morning, it does summarize it in that way. So one thing, if it was of interest to estimate what this error variance was, sigma squared, the first thing we need to know is what is called a residual. And a residual is nothing more than whatever the observed value of y is, right? We have a real data set, so we have real y's. If you just take y minus the predicted value of y, right? This is what y hat is, whatever our model is going to spit out. Okay, so of course this y, this observed value of y, I'll just say pick this first observation here, right? This guy has an observed value of y and a corresponding value of x. So y, in this case, just for the first person, so think about residual 1, e sub 1, would just be 77.9, and then to get the fitted value of y, we would go up here to our regression equation, right, the equation of our line, and once we fit our line, right, these, our estimators are known values, and so we have to stick in the x value that corresponds to the y value here, right? And once we do that, our regression model spits out a predicted value of y. And so a residual is nothing more than the observed value of y minus the predicted value of y from our model. Okay? So another result, the sum of the residuals is going to be 0. Not super concerned. So a residual sum of squares, it's also known as an error sum of squares. So residual sum of squares, might also see it as SSE for error. It's just the sum of the squared residuals, right? The residual is y minus y hat, and specifically in that order, you don't want to flip-flop that order. Y minus y hat, take the residual, square it, and do that for each observation. Sum them all up, and that's called the residual or error sum of squares. And if you divide that by n minus 2, okay, technically this 2 is the number of parameters in the model. Okay, in simple linear regression, we just have an intercept and a slope parameter, beta naught and beta 1, so we just have a 2. Okay, and this is, if you divide it by that, which is technically called its degrees of freedom, then you have a residual mean square or a error mean square. Okay, so this quantity divided by n minus 2, n minus number of parameters, is the residual mean square. Okay, and that is an unbiased estimator for this variance. And of course, if you recall, standard error, that's nothing more than the standard deviation of an estimator. Okay, so the residual standard error is just the square root of the error mean square, or the residual mean square. Let's go ahead, that's a lot of talking. Um, let's go ahead and look at an example. So um, if you would like to go ahead and try this as I go along, it'd probably be helpful for you. You need R up, and at this point you just need the ANOVA and regression code. So maybe I'll give you a minute to pull that up, and also while we're waiting for people to pull that up, if anybody has any questions that they'd like to go ahead and ask, now would be a good time. All right. Uh, Anybody still working on graphs? Oops. Oops. What just happened? Oh, there we go. Okay. All right. So the first thing that we need to do is we worked with this iris data set briefly when we did ANOVA, and it's a one we're going to go ahead and work with now just to see an example. So copy the first line, attach iris, put that into R, and now once you do that, if you put iris, you should get this data set that has 150 observations. Right? It's got kind of 5 variables. 4 are kind of numerical variables observed on each flower, and then the 5th variable denotes the species of flower. Okay, so if we go down here, we can see we have regression. So the first thing that I want to do is, in this case, right, there's more than 2 variables here. So what I want to do to make it a simple linear regression model is I just want to focus on 2 of them, petal width and petal length. Okay? So if I copy paste that code into R, plot, petal width, petal length, plot function, that's how you can get a scatter plot in R. Okay? And so we can clearly see that there does appear to be a relationship between petal width and petal length. As a petal's width gets longer or higher, then the petal length goes up. Okay, so there does appear to be a positive relationship between these 2 variables. And just looking at it, it looks like it could be reasonable to fit a straight line through this set of data. There doesn't appear to be a terrible amount of curvature or some strange wiggly pattern, right? Or some bimodal or unimodal pattern where it goes up and back down. Okay, so that's a nice look to see that the petal width and petal length seem related. So what we can go ahead and do is we want to create a linear model, LM, and we want our Y value, you always put the Y value first, to be petal length. So that's going to be our response variable, kind of the variable that we're interested in. And so we would like to use tilde petal width, our X variable, okay, our predictor variable, in order to gain information about a petal's length. Okay, and one good thing is to give it a name. Here I've given it the name reg.model. You can call it anything you want, but usually we're going to use this in other things. So instead of just typing this in it by itself, if we call it something, that allows us to use it in further functions without having to retype the whole thing. Okay, and so let's see what that looks like. So it looks like, so what it's doing, this linear model function, recall the goal is to figure out what the intercept, beta naught hat, and the slope, beta 1 hat, what the best possible intercept and slope is, right? The best possible line that I could fit through this data point, through this set of data points. And we do that through that least squares method, right? Minimizing that Q function. And that's what these two values are. R is doing that minimization for us, okay? And it's spitting this out. So we're never going to have to do that by hand, but it's nice to understand what these values are and not just kind of blindly accept them for, magic output from R, okay? So, so our fitted regression equation, right, is going to be, right, petal length is equal to the intercept 1.084 plus because the slope is positive plus 2.23 times petal width. Okay, so that is our fitted regression equation. Again, petal length here, this is y hat, right? And then this is x. So this is the equation of my regression line that we haven't shown here, but we will in just a minute. Okay, so anytime I want a prediction for a petal's length, all I have to do is put in, say, an observed or a future petal width, and it spits a number out, right? Just 1.084 plus 2.23 times whatever petal width I plug in. Okay, so we would like to see what that regression line actually looks like, and that's what this line does. AB line reg.model. Okay, so you can ignore the last two things. If you already have a scatter plot up like this, which we did from plot, if you use this AB line function and you put as the first argument whatever you called your regression model, then it's going to put the line of the regression model. Okay, so this is our line of best fit, right? And so of course, right, this is 1.084, right, and the slope is 2.23. So let's see if these have interpretable meanings in the context of this problem. So first off, the intercept, right? The intercept is interpreted as when we have a petal width of 0, right? So kind of this goes away. Petal width of 0, then the petal length is 1. So I think clearly that doesn't make any sense in this context of this problem to think about a petal's length when it doesn't have any width. Okay, so that doesn't make any sense. However, as I've said before, the slope parameter is usually the one that's pretty much always going to be of interest. And so whenever we increase a petal's width by 1, right, we increase x by 1, then the response variable, the petal length, increases by 2.23, okay? And I think it's easy to flip that interpretation to begin with, but whenever we increase this by 1, right, just think about plugging a 1 in here, right? Before, when this was 0, right, if petal width is 0, then all I have is this intercept, right? But think about plugging a 1 in here. Well, what happens? Well, now I add 2.23 to this 1, right? I'm adding that to petal length. So whenever x goes up by 1, y goes up by beta 1 hat, which is 2.23, right? So whenever we go from, say, 0.5 to 1.5, we should go up by about 2, right? So 0.5 was about 2, so just automatically I should know that the value here should be about 4, right? And we look, and there it is, right? The slope is about 2, a little over 2. So whenever I go up by 1 on petal width, petal length goes up by 2. Any questions on anything so far? Okay, again, if you do, just throw them in there. Okay, so this code here, I'll go ahead and show you this. These last 3 lines right here, that is what gives us our estimator for sigma squared. Okay, so again, this is the residual sum of squares, or the error sum of squares. And what we have here is we have a sum of the squared values of the residuals. Okay, this is just y, petal length is y, and then this predict reg dot model, that's what gives us y hat. Okay, so we have our residual sum of squares, we have our degrees of freedom. Okay, this length, this is just n right here, n minus 2. So error sum of squares divided by n minus 2, as we just saw a few minutes ago, that is our unbiased estimator for the variance. And it looks like about 0.2 for the, and specifically for the error variance, right? Sigma squared. Okay. Let's continue on in the notes a little bit. So, right, we have predictions for these, right? Throw a hat on top, and that's our least squares estimates. But as with other things, we might not just be happy with a single point estimate. We might want a range of values that are plausible for the intercept and slope instead of just a best guess value. So, right, we know the distributions for these things, right? We know y has a normal distribution under our assumptions, and that these beta naught hat and beta 1 hat also have normal distributions. So knowing that they have normal distributions, we can create confidence intervals, right? And that sort of thing. So kind of like before when we were doing a confidence interval for the mean, okay, we used the t-distribution, which again is some named continuous distribution whose probability density function we did not look at, but nonetheless we said that the quantity, a specific quantity related to the mean, had a t-distribution, and we were able to use that to construct a confidence interval. It's very similar for this. We know that beta naught hat, right, the point estimate, has a normal distribution. So if we basically subtract off beta naught hat minus, or sorry, beta 1 hat minus beta 1, divide by its pretty much standard error, then we come up with the t-distribution. And knowing this distribution, we can create a confidence interval. Okay, but we're not going to do this by hand. We're going to do it in R. Again, if hopefully you kind of followed back when we were originally going over confidence intervals, kind of that method of we had a quantity that contained both the parameter and the point estimate for the parameter. We basically subtract the two and divide it by the standard error, or estimated standard error, of our point estimate, and we knew the distribution for that quantity, and we could basically flip that around in order to construct a confidence interval. So, and we're doing the same thing here, and it has a similar form to the confidence intervals that we did for the population means. Point estimate plus or minus a quantile times a standard error. It has that very nice classic confidence interval form. Okay, so, and the interpretations are back to our chapter on confidence intervals, same type of interpretation. Okay, so let's go ahead and calculate that. So this conf int function right here, this is what gives us confidence intervals for the least squares estimates. So beta naught hat and beta 1 hat, the estimated intercept and the estimated slope. And if you just put level equals something, that's like putting conf.level in some of the t dot test and the prop dot test, right? This is telling it instead of a 95% confidence interval, you want a 92% confidence interval. And so the argument is just whatever you called your simple linear regression model, okay, which was reg.model. So this is telling R that I want 92% confidence intervals for the intercept and the slope. And I believe, yes, each of these are individual 92% confidence intervals, okay? Right, yeah, they're individual, they're not family-wise, kind of like the Tukey was, such that we were 90, 95, or in this case 92% confident of all of our confidence intervals. These are kind of individual, okay? So let's see if these have nice interpretations in this case. But so anyway, we are 92% confident that the mean value, the mean petal length is between, I'll just round, 0.95 and 1.2 when the petal width is 0. Okay, that is how we would interpret this first confidence interval, the confidence interval for beta naught hat. That's how we would interpret it in this problem. As I've said before, the intercept is not meaningful in this problem. Other problems it could be meaningful, and this is how you would interpret it, okay? So the more meaningful one is the intercept, or sorry, the slope. We are 92% confident that for every, I don't know the units, every 1 unit increase in a flower's petal width, right, x, a flower's petal length increases between 2.1 and 2.3 units. Okay, maybe it's inches or millimeters or whatever it is. And so this is the one that's useful. Okay, so for every 1 inch increase in a flower's petals width, we are 92% confident that the flower petal's length is going to increase between 2.1 and 2.3 inches. So from this confidence interval, this one thing that this confidence interval can do is answer the question: is petal width related to petal length? Okay, or do we have statistical evidence that a petal's width, or the petal width of a flower is related to the petal length of a flower? And we do, okay, because the confidence interval is completely positive, it doesn't include 0, we have evidence that there is a positive relationship. If this was completely negative, we would still have evidence, but we would have evidence that there's a negative relationship, right? So in that case, we would have a line that went from up here to down here. Okay, but anytime this confidence interval includes 0, that basically says, of course, in that case, if this confidence interval included 0, or if the slope, of course, the slope of 0 is just a horizontal line, and thinking about what that means that the petal, say the horizontal line was here, that just means the petal length is always 4 regardless of petal width, which in other words means petal width is not useful in predicting petal length, or is not related to petal length, okay, if we have a slope of 0. But we have evidence of a positive relationship, a positive slope. Okay, so another thing that we can do to determine if there's a relationship between y and x is, instead of looking at a confidence interval, looking at a hypothesis test that the beta 1 is equal to 0. Okay, so this hypothesis test is stating the null hypothesis is that the intercept is equal to 0, right? Meaning whenever x changes by 1, y changes by 0, right? Meaning there's no relationship between y and x, versus the alternative that the intercept is anything other than 0, meaning that there is a relationship. And of course, as always, you want to try to understand at least the very basics about the hypothesis testing, how we conduct it. When the p-value is small, specifically smaller than the significance level alpha, which is right almost always set to be 0.05, we reject the null hypothesis and say that we have evidence of the alternative. So in this case, a small p-value would be saying that we have evidence that the intercept is not 0. We have evidence that there is a relationship between y and x. Okay, so this summary function, summary reg.model, summary reg.model, this is what allows us to get the p-value, okay? So let's see what that looks like. Just type in summary reg.model, copy paste. It spits out a lot of stuff here, okay? And so we can see here, this is our intercept and this is our slope. So beta naught hat, beta 1 hat, our least squares estimates. And so the hypothesis test is over here. Remember this it looks very similar, this funky probability greater than absolute value of t. Okay, before when we were looking at ANOVA, this said probability greater than f. Okay, unfortunately it doesn't just say p-value, so you have to know what you're looking for. This is the p-value. Okay, so this is the p-value specifically testing whether beta naught is equal to 0, and this is the p-value for a completely separate hypothesis test that beta 1 is equal to 0. Okay, and so we can see in both cases they're extremely small. Okay, meaning that we have evidence that beta naught is not equal to 0, and we have evidence that beta 1 is not equal to 0. Now, in general, testing whether the intercept is equal to 0 is usually not going to be of interest to us. This is what's going to be of interest to us, testing whether the slope is equal to 0, because that is what tells you whether x is related to y, right? Whether x, the predictor variable, is useful in predicting y. So the decision, again, this is a very small p-value, okay, right? Let's just go ahead and say, well, actually, I want to relate it to this confidence interval. So recalling what would be the alpha related to this confidence interval, it would be 0.08, right? 0.08 would be the alpha that corresponds to this confidence interval. So the p-value, which is basically 0, right, 2 times 10 to the negative 16th, is less than alpha, the significance level. I'll go ahead and call it 0.08. So we reject the null hypothesis that beta 1, I'll just put it like that, is equal to 0. Okay, and we have evidence that I'll say this, that x, right, petal width is useful in predicting petal length, right, which, well, y, right? And notice we got the same decision, right? We, in the confidence interval, the 92% confidence interval said, right, it's useful, right? And the hypothesis test at the 0.08 level of significance also said it's useful. And so anytime you do a confidence interval and a hypothesis test that correspond to one another, and you use the same level of significance, the decision will always be the same. Okay, they will always go to the same conclusion. So you could use either one of those to determine whether we have statistical evidence of a relationship between y and x. Okay, so the next thing to talk about is confidence intervals and prediction intervals for y for a given value of x. So basically, we pick a value of x, we set it equal to some specific value, and we want a confidence interval or a prediction interval for y. Okay, so for example, right, we might be interested in, right, for some reason, when a flower has a petal width of 2, right, of course our estimate is 5.5 or whatever, somewhere in here, right? But we might not just want an estimate, we might want the range of plausible values, okay? Right, a range of plausible values here on the y-axis when we have a flower with a petal width of 2. So there's two ways to think about that. We could be interested in a range of values for that observed for a single observation. Okay, so if I want a range of values for a single observation for a given value of x, that is called a prediction interval. Okay, if I want a range of plausible values for this given value of x for the average value of y, okay, for the average value, that's called a confidence interval. Okay, so the difference in the terminology, recall average or mean, right? That is a parameter, okay? The average of the population for this value of x, that's like a mu, that's a mean. Whereas a prediction interval, just predicting a single observation, that's not a parameter, right? That's just I'm picking out a single thing, unit of the population, and I want to predict its y value for this x value. Okay, so that's just a prediction interval. So, of course, like the other confidence intervals, etc., that we've done, the general gist is understanding its distribution, right? Where everything that we're working with kind of has a normal distribution. So since I know that, I should in some way be able to flip things around and get a confidence interval, right? So it's the same gist. The confidence intervals look a little more complicated, and I'm just not really concerned with their exact forms. Okay, but we can see here, this is the confidence interval, this is the prediction interval. Okay, notice here, confidence interval for the population mean, right? So confidence interval for the population mean when we have of y, expected value of y, for a given value of x. Whereas a prediction interval is it's a prediction interval for a new response, right? Just some single observation y for a given value of x. And so what we're going to see is that prediction intervals are wider for the same significance level. Prediction intervals are wider than confidence intervals. And that should make a lot of sense. If you remember x bar, right, the sample mean, if we know the population X has some normal distribution with mean mu and standard deviation sigma, then we know X bar also has a normal distribution, right? The sample mean, right? The average, the statistic has a normal distribution with mean mu, same mean, but the standard deviation or standard error is sigma divided by square root of n, right? So the standard deviation is the same as the standard deviation of the population, but divided by the square root of the sample size, right? So thus it has a smaller standard deviation, less variability, okay? So averages, right, sample mean has less variability than the population. So it only makes sense that when we do an interval for the mean, right, it should have less variability than the interval for a single response value, right? So this is like an interval for a single value. This is an interval for the average value. So this should have less variability. And having less variability basically means, right, remember the common form point estimate plus or minus quantile times standard error, right? Having less variability means that this quantity is smaller than this quantity. Thus, right, we're adding something smaller and subtracting something smaller to the middle value, which means the confidence interval is going to be more narrow. So let's see what that looks like. This predict function, okay, this is how we get confidence intervals and prediction intervals. The only difference on how we tell R whether we want a confidence interval or a prediction interval is this last argument here. Interval equal conf tells R that I want a confidence interval for the mean. Interval equal pred means I want a prediction interval for a single observed Y, okay? This argument here is what X value do I want this interval at, right? Where this interval is for a single value of X, right? So before I was saying, right, maybe I want intervals for when X is 2, okay? If that was the case, then I would just plug in 2 right here, okay? 2. But what this function is doing, this is saying I want intervals for the X value to be the average X value, right? Mean petal width, that is the average X value. So I want these intervals to be for when the X is the average X. And we can kind of go ahead and see what that looks like. The average petal width is about 1.2. Okay, the average petal width is right here. So this is saying I want these intervals to be right here. Okay, and the first one that we're going to calculate is the confidence interval for the average petal length of a flower that has a petal width of 1.2. Okay. Okay, and that's what this is going to do. So reg.model, that's whatever we called our simple linear regression model. We leave that alone. This is X, right? X is equal to 1.2 pretty much, right? X is equal to the average value of X. So just think about replacing this with 1.2 or whatever other X value the problem gives you. So you would have to change this to be whatever X is called. And of course, whatever value of X you want, you would have to replace with this. And of course, also level is equal to 0.9. This is saying we want a 90% confidence interval. Okay, but that should be the only things you should have to change depending on the problem. Okay, we can ignore this lower bound, upper bound. Okay. So this is our confidence interval, and specifically, we are 90% confident, right? We used level is equal to 0.9, 90% confident that the average, right? This is a confidence interval, so it is for the average. We're 90% confidence that the average petal length, that's why, the average petal length of a flower that has a petal width, right? That's x here, petal length. Right, that's our response variable. I'm not going to capitalize it. That's our response. Petal width is our predictor variable that has a petal width of, what was it, basically 1.2, and I'll put in quotes, this is the average petal width, okay? So technically it's a confidence interval for the average petal length for a flower that has an average petal width, but specifically it is for a flower that has a petal width of 1.2 because that's the average. Okay, is between 3.7 and 3.8. That is exactly how we would interpret this confidence interval. So we're 90% confident that the average petal length of a flower that has a petal width of 1.2 is between 3.7 and 3.8. Okay? So this fit, that's the point on the line. So that's our point estimate. That's our y hat when x is 1.2. Okay, so it would be very easy to show if you put 1.2, plug it in right here, then this plus this times 1.2 is going to be 3.758. Okay, so that's the y point on the line when x is 1.2, or well, specifically this. But this is the confidence interval for that average value of y. Okay. So instead of just saying when a flower has a petal width of 1.2, I predict a length of 3.758, I would instead say I'm 95% or 90 in this case percent confident that the width is between 3.7 and 3.8. Okay, so that not only tells me that gives me a range of values, right? So that I can make more informed decisions, because maybe it could be that the line still goes through here, but there's a lot of variability, right? Which is bad. But we can clearly see it just goes between 3.7 and 3.8, which is, right, a very narrow margin, which is nice. Okay, the other interval, the prediction interval. Again, I want to do a 90% prediction interval for, and now it's because it's a prediction interval, it is for a single new observation. Okay, a 90% prediction interval for the petal length of a single flower, right? Just a random flower that has a petal width that is the average petal width. Again, a petal width of about 1.2. And again, this should be wider because it's not an average, it's just a single observation, so there's more variability in predicting a single observation. And notice instead of going between 3.7 and 3.8, it's between, right, about 3 and 4.5, much wider. Okay, it is much harder, say, to predict a single observation than to predict an average of observations. So, interpreting this, so we are again 90%. I don't want to confuse you, but technically a prediction interval is a probability statement. Okay, remember all of the confidence intervals that we've ever done have never been probability statements because they've been statements about like means and true values in the population that we simply just don't know. This is not some true value, right? Because we're not, it's trying to predict a single value, right? When we have a certain X value. So technically, it's like having just the population distribution and just thinking about of all the people that have this X value, right? I want 90%, right? My confidence interval, well, in this case, my prediction interval to cover 90% of those. And so technically this is a probability statement. If you want to keep it like this, you can, but technically, there is a 90% chance, probability, that the petal length of a, right, kind of emphasize a random flower that has a petal width of 1.2 is between, I'll just make it easy, 3 and 4.6. So basically, based on the model, 90% of flowers that have a petal width of 1.2, 90% of them have petal lengths between 3 and 4.6, basically. So if 90% have petal lengths between 3 and 4.6, then if we pick out a single flower that has this petal width, then there's a 90% chance that it's going to have a petal length between 3 and 4.6 because 90% of the flowers do, okay? So kind of two different ways you can look at probability. However, never put probability here when we're talking about parameters, average, right? Because there is some true average petal length if we were to observe all flowers that have petal widths of 1.2, we could actually take and find the average. So there is some true average out there, and that's why we can't say probability, because this confidence interval either contains it or it doesn't. So questions? Haven't really gotten any questions. So this code right here, I'm not expecting you to ever replicate this code for anything. All of this that I've done, you would have to replicate for homework to practice, and you might need to use for the final exam. This code I just want to show you, okay? So what this is going to do is, with my same data set and my same regression line, I'm going to put the 90% confidence interval and the 90% prediction interval kind of for each value of X, so you can kind of see the difference, okay? And so we can see this dotted black line. Those are all of the 90% confidence intervals. So again, the confidence interval is from here to here, right? We're 90% confident that the petal length when a petal width is 0.5 is between here and here, right? When it's 1, we're 90% confident that it's here and here, etc., going up and down. But when I predict a single observation, a single flower, instead of talking about an average, whenever I say, again, look at a petal width of 0.5, now I would say that there's a 90% probability that the petal length is going to be between right here and here when a flower has a petal width of 0.5. And again, 1.5, I'm 90% confident, 90% probability that the petal length is going to be between here and here. So you can kind of see the difference, right? The prediction interval is much wider than the confidence interval. But you won't have to replicate that, but hopefully that's a good picture to show you the difference. This is a nice picture Just some random example. X in this case is mid-year evaluation and Y is year-end evaluation. So I just want to focus on the picture. So, right, this is X, this is Y. And so you could think about this. This is our regression line, okay? So just kind of ignore that it's a curve and not a straight line for right now. So this is basically equivalent to fitting a slightly more complicated model. But all of those assumptions about the error term, that's what this is a good picture for visualizing, right? We assumed that those error terms are all right, normally distributed, independent and identically distributed, normal distributions with mean zero and a variance sigma squared. So because we know that, we know the distribution of y, right, go back to that. Right, we know the distribution of y, right, and they all have the same variance, and it's going to be normally, the y values are going to be normally distributed with this mean, right? So the intercept is the same, the slope is the same, the only thing that changes is the value of x. And so looking at this picture, that basically means, so when I have a x of 50, right, I've got a normal distribution for y, right, centered at this point, right, beta naught plus beta 1x, right, and my variance is sigma squared. When I've got a x value of 70, I again have a normal distribution of y values centered about beta naught plus beta 1x, right? The only difference here is I'm plugging in x of 70 instead of x of 50, but notice I've got a normal distribution of values, right? So I think my values are going to be in here somewhere, right? For y, my y values I believe are going to be in here, but of course I believe they'll be centered here. And it has the exact same variability. Notice the curve is the exact same. And likewise, this curve is the exact same as this. The only difference is it's shifted up on the y-axis because it is centered at beta naught plus beta 1x, and I'm plugging in bigger and bigger x's. Hopefully that's just, I think, a good illustration of the assumptions and what we're kind of trying to do of relating x to y. Right? We believe that for any given x value, that basically the y values are going to have this nice normal distribution with the same shape, same variability, and the relationship is just we have some intercept plus some slope times this x value. All right, that's basically the material that I wanted to cover today. I sent you homework 5 and the solutions. I might, I would recommend going ahead and trying it for yourself. You have the solutions as well, but trying to get all of this output, you should be able to pretty much get all of this output yourself. There's looks like a couple things down here we didn't quite talk about. But try to get all of this output yourself, and maybe I will start next time and try to go over some of this problem just to give you another example and make sure that you are confident in using this code on a different data set. Of course, this data set, Fuel, it should be on Blackboard, okay? And so you should have what you need to complete most of this stuff, okay? And I can go over it at the beginning of next class. But if you've got any questions, there's still a few minutes left of class. I could try to answer any specific questions that you might have relating to the linear regression or the course in general. I'll wait for a couple minutes to see if anybody's going to type me some questions. Uh, Hopefully the recording worked properly, and I will be posting it on Blackboard since I realize that I can do that now. And I will email you once it is posted, provided that it recorded properly. So there was a pretty good turnout for this lecture, so I do plan on continuing to do the live lecture, although nobody really asked any questions, so I'm not sure how it's different than a recorded lecture, but I will continue to do another live lecture on Thursday uh, to give you the opportunity to ask questions if you have any. Give it another minute if you happen to think of a question or are typing a question that you might want to ask. Otherwise, I will see you for the Thursday's lecture.